So the last section of our geometry unit is really kind of tying together the last two things that we've talked about. So we're going to take a look at area and volume again, but this time consider it with that sense of scale. And so by writing things as, or drawing things or considering things that are similar, and we have a scale factor. And so this one we have here is a smaller rectangle and a larger rectangle, and the larger rectangle is increased by a scale factor of 2. What you can see is that each length of the sides, or widths, right, is scaled up by a power of 2. What we're trying to do with this is figuring out how this scale factor affects area overall. So if we have all the numbers, we can do the calculation, right? We could take area being length times width and calculate what the area is of the small rectangle and the large rectangle. What we can see is that we didn't double the area, we actually multiplied the area by 4. And so the relationship between the small rectangle's area of 15 centimeters and the big rectangle's area of 60 centimeters is 4 times. But what we could think about, it's actually my scale factor increased in 2 dimensions. So 2 squared would be 4. So an increase of a scale of 2 increases the area by 4. You have to use the scale factor in 2 dimensions, so you essentially square the scale factor. We're going to write this out in a way to hopefully make some sense of it. So we want to know the new area. What we're saying, that is always going to be the original or old area times the scale factor. And the key thing here, that scale factor is going to be squared, right? 1 for the length, 1 for the width in 2 dimensions. So you could write this out in a formula. So the area 2, or the second area, the new area, would equal the original area, A1. We haven't seen subscripts by variables, but that's something that gets done in physics and other things like this, geometry, times the scale factor squared. And so I put this box in here to give us somewhere to kind of summarize what we're looking at with this. Let's try a few of these. So this page is all about area. So this triangle, should know my shapes by now at the end of a geometry unit, this is increased by a scale factor of 5. And so we have all the information that we need to calculate this. So we could do the area of this is 1/2 the base times the height, and we'd get an area of 6, whatever units squared that is. And the area of this one would be 1/2 the base times the height. I think that third side is there to make sure that you see how each side is multiplied by 5, and also could prove that these are similar triangles, because that would be an important part of this. We'd end up with 150 units squared, whatever that is. So let's check, this thing that we were saying without actually calculating everything. If we had the original area times the scale factor squared, right? That should end up to be 150. So 6 times 25 on your calculator, it would be 150 units squared. And all I'm doing with that is checking the logic that we made up here with our kind of equation that we derived from looking at this. So this one about a hexagon, we never figured out areas of hexagons, thank goodness. We don't really need to know. If we know that we have an 8 centimeter squared area, and we're going to increase that by a scale factor of 3, even if we don't know the length of the sides, we could figure out the area of the new hexagon. So this would be area 1, this would be area 2. So area 2 is going to be my area 1 times my scale factor squared, right? Area 1 is 8 times my scale factor, which is 3, and I'd be increasing both my length and my width. This is in 2 dimensions because that's what we can calculate with area. So that should allow me to calculate 8 times 9, or 72 centimeters squared. My new area would be 72 centimeters squared. We're going to do the same thing here with volume, and then we have a few questions that are kind of mixed up, which makes you kind of stay on your toes. So we're going to do the same thing about scale factor and how it affects volume. So we can have a box that's increased by a scale factor. In this one, it's asking you, what is that scale factor that it's increased by? And if you know that, could you fill in the other sides of the box? So if we go with just this one length that's given to us, we can see that it's scaled up by a scale factor of 3. So completing the other sides of the box, I could figure out the dimensions of both of the boxes. If I want to go at this in kind of an exploratory way, like the last one, volume would equal length times width times height. So 3 times 6 times 2, and I can calculate the volume of both of these rectangular prisms or boxes. So 36 units squared, whatever, or cubed, whatever that is. And this one would be, the volume would be 9 by 18 by 6. And so that works out to 972 units cubed. So what's going on between these ones is that we've got an increase, not in 2 dimensions, but in 3 dimensions. So the new volume, to go from one to the other, I can show you the math in the middle. That is kind of the shortcut when we don't have all of the dimensions given to us. The new volume will be, and I'll call that V2. Let's just go straight to that kind of nomenclature. We'll write it out in a little bit here. So the new volume would equal the original volume times the scale factor, this time not squared, but cubed. Let's check the math on this. So I should be able to get to my 972 by taking 36 and multiplying it by 3 cubed. So use that y to the x button on your calculator. That's 36 times not 9, but 27. And I should get on my calculator, or I did, 972. So this gives me a go between these concepts. So why it's a cubed factor is that you're increasing not in 2 dimensions, but in 3 dimensions, right? Height, depth, and length. And so in this one, you could figure out your new volume would equal your original volume times your scale factor but that scale factor is in all 3 dimensions. So that's where that cubed comes from on your scale factor. If I write this as a simplified equation that I can look back to and hopefully make sense of, I would end up with something that looked like what I already written before, like that. So let's try these. These next ones are mixed and matched. Some of them are area, some of them are volume. The only difference is knowing that when it's area, that's 2-dimensional, so your scale factor is squared. And when it's volume, that's 3-dimensional, so your scale factor is cubed. So we have a box with volume 1.3 meters squared. It's enlarged by a scale factor of 4. What is the new volume? So in this one, I would say my V2 is equal to my 1.5 times my scale factor cubed. I can use my calculator. Remember that y to the x, what this actually means is 4 times 4 times 4, right? So my calculator allows me to say that this is 96 meters cubed. My original volume was in meters cubed, so my final volume will be in meters cubed. Okay, so the next one is a scale factor that's used in the metric system, and there's a few of these in your homework. So we have a canvas that is measured in meters, but we want to know how many square centimeters this is. Oftentimes art is measured or evaluated or valued in its size as a beginning point. And so, sometimes you get those in the wrong units. So we have an area of this. We could figure out the area originally is 2 times 1.5, or the original area is 3 meters squared, right? We want to know how many square centimeters this is. This is a scale factor of 100, right? We have 1 meter would have 100 centimeters in it. So we're bumping it up 100 times. And so it's sort of a sneaky one in the metric system. Changing units is implying a scale factor. So if we've determined our original area and we've determined our scale factor, we can now use, like what I had done before, my secondary area, which is going to come out in centimeters, which is handy, would be 3 times that 100. And remember, we're doing area, so that's the squared scale factor. So this would be 30,000 centimeters squared. There's actually one in your homework that goes the other way, but I make sure that I give you the scale factor. It's a lot easier to bump things up in size than it is to scale them back. So I've tried to give as many hints and tips in that one. Okay, so we've got the last two here. So we've got a 3D model, printed model. It's supposed to be enlarged by a factor of 20. It has, so the model has a volume of 0.16 meters cubed. What would the new volume be? And so we know my V1, we know my scale factor, right? And the key thing here is that we're talking about volume. So that's going to cube my scale factor. My final volume, the actual volume of this thing, when it's actually built, not just 3D model printed, would be 0.16 times 20 cubed, right? Following that pattern, following that model. We don't have to know all the dimensions to calculate this secondary volume or this new volume. That's going to be 1,280 meters cubed. I left a deceptive amount of space for that one. The next one is a bit of a picture, which is kind of fun to do. We have a small box and a large box. You can see that it's scaled up, right? 10 and 30, it's scaled up by a factor of 3. That's the first question. The scale factor of this is 3. What's the volume of the larger box? Remember that means that my scale factor is going to be cubed, not squared, because we're not talking about area. So my secondary volume would equal my original volume, which it gave to me, so 500, times my scale factor cubed. This tells me that my secondary volume is 13,500 centimeters cubed. It says, this is a bit of a challenge question, how many times bigger is the larger box? And so we take that 13,500 divided by the original to figure out this box is actually 27 times, I'll write it out in words so it's not too confusing, times bigger. Big box is 27 times bigger. If we take a look, we already knew that. We knew that this, right, that's what this last section is showing us, is actually how many times bigger these things are. The key thing is that if you're scaling up a two-dimensional thing, it's the scale factor squared, and if you're scaling up a three-dimensional thing, which volume is, it's going to be cubed.